All right, this is going to be a continuation of R2DSP Project 4 demonstration part 4, where we're talking about cascaded LC-Pi circuits. In the previous video, I did circuit analysis to derive the transfer equations for the LC-Pi circuits, or LC-Pi filters, and I included some additional resistors to help me out with damping and to include and to make some, for dampening to make the filters easier to design. And then I demonstrated them in Code Composer. But I want to go back into MATLAB and do a more in-depth analysis on each of these filters, just like how I went back and did an in-depth analysis in MATLAB for the RC Pi filters. So we're going to start off with the cascaded bilinear LC Pi low pass filter. So I set the cutoff frequency to 3000. So if I go to 3000, go up 3000, down a bit. It's gonna take a while. All right, so it's approximately around negative, it looks like 18. And we would expect an attenuation around negative 18 because like I mentioned in the previous video, the LC Pi circuit or LC Pi filter has 3 LC components. It either has 2 inductors and 1 capacitor, or 2 capacitors and 1 inductor. Since it has 3 LC components, it'll create a third order filter. And I'm cascading 2 of these together. So if I cascade a third order filter with a third order filter, I'll end up with a 6th order filter. Now, a first order filter will attenuate at the cutoff frequency of negative 3 dB. And since I'm cascading essentially 6 first order filters together, the attenuation of the cutoff frequency will now be negative 3 times 6, or negative 18, which is why when we see at the cutoff frequency, we have an attenuation of around negative 18 dB. This is for the bilinear cascaded low pass filter. So here, this is with now impulse invariance. So similarly, if I go to about 3000, go down to 3000. Oh, skipped it. So over here, we see that it's close to. Oh, go back. It's close to 18, attenuation of 18. You also may have noticed, just like how we observed with the cascade RC filter, once you start approaching the Nyquist frequency right here, it sharply cuts downward. And it sharply cuts downward because we've lost linearity because we're starting to approach the sampling frequency's Nyquist frequency. So you can compare it with the impulse invariance, which continues its smoother attenuation. So since I have the range, I think I have the range. Can I go up 30? No, I do not have the range. I can't see. Maybe if I go to about 2000 here, and then about 20,000 down here. That's going to cut in close though. So if it's a 6th order filter, we should have expected a attenuation rate of negative 120 dB per decade, because it's negative 20 dB per decade multiplied by 6 for a 6th order filter. But that happens after the cutoff frequency. So that would happen after 3 kilohertz. But unfortunately, my sampling frequency, I didn't choose to be large enough to actually see 1 decade from that. But over here, you can see that this is not going to follow roll-off rate over here, because we lost nonlinearity. It's going to just get attenuated extremely quickly, as you see here, negative 450 dB. So it gets attenuated really quickly. So those were the low pass filters. So this should be, here we go. No, not that one. So this one. There we go. This is going to be the bilinear high pass filter. Yeah, there should be here. All right, I didn't include the impulse invariance high pass filter because we didn't use it, because you don't want to design one, but I should have it in theory. I just need to uncomment these out. So I should have the high pass filter for impulse invariance in theory, even though I did not use it. I guess it's a good practice in Laplace transformations and all that. So this is going to be high pass filter using bilinear transformation, which is what I use for both filters, since you can't actually use impulse invariance for both those cases. So okay, cascade bilinear LPF, cascade HPF. Okay. Oh, I forgot to write it down, but this is going to be impulse invariance. This is going to be impulse invariance right here, I believe. So you notice right away between the two of them, well, the cutoff frequency is 1500, so I should expect at 1500 I should expect a gain of -16 about, or -18, just like before, because we have -3 dB multiplied by 6 because it's a 6-order filter. So we see that's around 18 over here. Now, if we look at the high pass filter, I have a feeling it might not be scaled correctly, because I'm pretty sure that's why I keep running into issues with using the high pass filter, because it doesn't get scaled correctly. Yeah, so if I look down here, all right, so it looks like around -12, which -12, if I think about that, sounds like a 4th order. So is it a 4th order? No, it should not be a 4th order. It should not be a 4th order, because it's a 6th order, just like before, because I have the impulse response. So if no, it shouldn't be, because I have the numerator, LC numerator, and RC RL numerator. Oh, this is for bilinear though. I'm looking at impulse response, high pass filter. Yeah, I have the RC and then I have the LC. Convolve them together, and then I should have cascaded them. So cascaded impulse HPFs. Yep. So I should have cascaded them together. So it should have been the same. It should have been a 6th order system. So I should have expected an attenuation around -18, just like before, but I didn't. Instead, I see an attenuation of, oh, not that one. I see an attenuation of -12. So there's obviously some scaling issue here, because it looks like this one has a very sharp roll-off rate going down -250, which you'd expect from a 6th order filter. It has a sharper roll-off rate. This roll-off rate doesn't look as sharp, so I'm pretty sure there's going to be another scaling issue with the high-pass filter, and that's because you don't want to use the high-pass filter, design a high-pass filter using impulse invariance, because you run into these sorts of issues. So with that in mind, that's the high-pass filters. Now we can start combining them. So this is the cascaded bilinear. So that means it's going to take the bilinear low pass and the bilinear high pass and cascade them together. So if I look for where my cutoff frequency is, it should be 1500 on this side as I move this over to about, yeah. So this is supposed to be 1500. So this is supposed to be -18, but notice how it's -23. This is approximately 3000. I don't want to spend too much time here, but it's also approximately -23, when they should both be about -18, as we'd observed earlier in the separate filters. So this is -18. And just like before, if we look at the high pass filters, so did I choose? I think I chose the bilinear one to observe first. So if I have the bilinear one, which I had right here, which is at -18, and I have the bilinear high pass filter. If I go to 3000, notice how there's an attenuation of -5. So that's where this extra -5 attenuation is coming from, because the high pass filter hasn't reached well within the pass band. So it's going to attenuate this signal by an extra 5 dB, along with the negative 18 dB attenuation from the other filter. Similarly, on the other side, if I bring up the bilinear on this side, so this one should be 3000. So this one's 3000 is about 18, but you have to add that negative 5 from the other filter. Similarly, if I take this and go to 1500, there's an attenuation of about negative 5, which is why this one also is attenuated by an extra negative 5. And you see this nonlinearity that appears here because the roll-off rate's going down smooth and then it sharply turns downward. And also, if you notice here, apparently there's a little stem here, or little peak here. It looks to be 28 hertz. I'm not exactly sure why. This is here at 28 hertz, and also this should be continuously rolling off, and that should not be constant. But that is because of this. Probably these errors in the bilinear high pass filter are probably causing this. And these errors are most likely caused by precision because we're getting really small into the decimal places. So this is probably where this error is coming from. So now if we look at the impulse invariance. So impulse invariance is actually a combination of bilinear transform and impulse invariance, because we only use the impulse invariance for the low pass filter. For the high pass filter, we can't use impulse invariance, so we just use the bilinear high pass filter again. And as we observed earlier, where's the bilinear high pass filter has some errors when you get into these frequency ranges, which is why you see these errors reflected into the cascaded impulse frequency response here. So these errors, like I said, are likely due to precision because the numbers are getting small with a gain, with the dB gain of negative 200, which is going to be like every 20 dB is like 1/10. So that'd be like 10 to the negative 5 attenuation. So if we go back here and we look at the cutoff frequencies, we hear around 15 here, which is kind of, there we go, and 3000. Notice how, again, these are about, if we compare with the bilinear transform, the gains are about negative 23 instead of negative 18 because we have that minus 5 dB extra attenuation from the other filter because they haven't reached well within their passband. And that's because this passband is extremely narrow, because there's not enough time for the filters to both be well within their passbands to have a gain of exactly 0. So that's why you'll see those attenuations. So this is an in-depth look at the different frequency responses for the different filters and why they appear as they do with those extra attenuations. And as you, yeah, that's why those extra attenuations occur. And so this has been looking to a deeper analysis of the frequency responses of all these filters. A couple things to just generally remember is that impulse invariance, you can't design high pass filters. Well, you can design high pass filters, at least in theory, as I've done with the RC filter as well. But every time I design the high pass filters using impulse invariance, I can never get the scaling or the attenuation roll-off rate, all these factors quite right. I get the right shape, but I don't know if I'm just missing the scaling factor or something. But generally for high pass filters, we don't want to design with impulse invariance. So we use the bilinear transform. But the bilinear transform also has the problem that if you're close to your sampling frequency, you lose linearity. So when designing bilinear transform IIR filters, you want to make sure that your sampling frequency is much, much larger than whatever frequencies you're working with. And then as a general note, MATLAB is extremely powerful, and I use MATLAB a lot to do a lot of the polynomial multiplication by using the convolution command, which saves me a ton of algebra and possible mistakes. So by utilizing that, I can accurately generate, or I can accurately cascade equations, or accurately cascade multiple filters together with relatively little trouble, as long as I have the first order or the lower order filters designed, that I can just cascade them using the convolution command. So this has been a general or more in-depth look at the frequency responses of all the LC filters. These LC pi filters were originally third order filters, but I cascaded 2 of them to make 6th order filters. And then I cascaded the low pass, 6th order, low pass, 6th order, high pass to make a total of a 12th order LC pi filter.